Hi, welcome everybody. So this talk is called Breaking Enigma with the Power of Modern C++. Before I get into detail, a small intro teaser. I'm supposed to ask you a question, but with the lag, I think I'm going to have to answer it myself. Do you know who this man is? And of course, I can all hear you in the room saying, Alan Turing. Yes, we are all computer scientists or simulate in the room. So we all know this man, of course, and we all know that he's well known for working at Bletchley Park back in World War II, a place where the English Project Ultra, which was the English cryptographic unit, was set up to crack German, Japanese, and Italian cryptographic codes. If you've never been to England or to Bletchley Park, it's set up just about right there, a bit north of London. And of course, this is the machine that was invented by Turing at the time, or so we're told, the Bomba, the British Bomba. That was used to help to crack German codes. Some people call it a computer. Someone more pedantic would say that it's technically not a computer. It's an electro-mechanical computing device, but it's not a computer. Because computer is supposed to be general purpose and programmable. This machine is configurable. You can change some of the inputs, but you can't make it do anything else than what it's supposed to do, which is try to break ciphers, and especially one type of cipher. But Alan Turing would go on after the war to work on the ENIAC project, which was the first accepted computer, and it is a general purpose programmable computer. And of course, in this talk, we're going to talk about this interesting bit of German space magic that is the Enigma machine. So hi, my name is Matthew. I'm the tech lead at Products Development Studio. I work on a game called Answer 5 and 4, which is a strategy game set during World War II. So this is exactly my era. And I'm joined today by my co-host, Max, which you may or may not have seen earlier today. He's just right there. Say hi, Max. Come on, say hi. Hi. Okay, cool. Now you can go back to sleep. So, all right. Max and I are going to try to explain to you what Enigma is and how do we crack it. So what is this talk about? Of course, we're going to start by talking about cryptography. This is the main topic of this talk, and more exactly how to break cipher, and even more precisely, how did we historically break ciphers compared to, how would you do it today? And I swear at the end, there is some code. There's going to be some history, because, I mean, that's just me, but there's going to be some code at some point. So this talk started very simply. Someone in marketing on my game once published like a teaser on social media a couple, I don't know, 6 months ago, maybe a bit more, that was supposed to tease people about what the next expansion would be about. And it was done as basically an Enigma encrypt to that people break this and you're gonna get the teaser. But of course, the tweet also contained the key and basically everything you need to decrypt, like all the machine settings. And I remember having a discussion with marketing at the time, saying, "But what's the point, right? Like they can just go on an Enigma simulator online, just input some values, and then they'll get the thing out." So wouldn't it be more fun if they had to crack it? I mean, it's 2022, right? Like we can probably break Enigma on a Casio calculator or something. And after that, I was like, but can you actually? I have no idea. I assume that since it's like a mechanical device from like World War II, like something roughly like 80 to 90 years old, there is no way like it can stand to a modern computer, but actually could it? And this is basically what I decided to explore, and I'm going to share with you today. So yeah, if you want a really short summary of these talks, who would win? Like two nerds from World War II with like a lot of PhDs between themselves in cryptography, or me, a guy who kind of flunked my math class in engineering, but has the power of a machine that none of them could even dream of in the 1930s and 40s. All right. So the Enigma machine. We're going to take some time to explain to you a bit how it works, because if you've never really look at the subtleties of the mechanics, it is kind of hard to make an assumption of how hard it is to actually crack or not. So a bit of background. Probably the most overused quotes in the history of quotes in military games and the simulate. All warfare is based on deception, a quote by Sun Tzu, which is or is not a military thinker from ancient China. We're not even sure he exists. It might just be like a name associated to a collection of stories. But what he means is, if you've never been like a general or like me, an armchair general, I'm going to explain you real quick how that works. So the idea is that if you have bigger number than your opponents, usually you win. I had to close some JRs by fans a few times who were like, oh, but I have a smaller army with the enemy and I can't win. Like, yes, that's kind of the point. So, you know, if you can't have bigger numbers, try to hit the enemy where they don't expect you, and then you locally have bigger numbers. You trade like local superiority with better coordination. And a thing that like the modern 20th century invented was radio. Before radios, like coordinating huge units is nearly impossible. So you can't really do subtle maneuvers and try to outflank your enemy that much, because you risk that your entire formation will get lost in the woods. And that has happened a lot of time. So yeah, radio helps, and suddenly you can pull up like very complex movements and maneuvers and things like that. The blitzkrieg is one of the main things that people remember, but that is a game changer. The problem with radio is, as soon as the other side has figured what a radio is and know what frequency you're talking to, and they can hear your language, well, then they know exactly what you're about to do, and they can just wait for you and lay an ambush. And this has been done countless times in warfare. And this is usually not a place you want to be in. And so enters Enigma. It was invented really at the end of World War I, I think, just roughly toward the end, or maybe the year after. It's not entirely clear. The inventor says he thought about it in 1918, but the patent's actually from 23. And it was originally aimed at commercial markets. The idea was like, if you want to talk about like your trade secrets with another company or with another office of your company, and you don't want people like listening to your paying the local telegraph operator to know what you're talking about, you buy this piece of machinery, and then you can encipher whatever you're talking about with your other offices, with your like people that are traveling or whatever, and then the other companies cannot do any kind of industrial espionage. And what is really interesting about this machine, and we'll get into more details later, is that it's just a bunch of routers, some wires, like 26 lamps, a keyboard, and a battery. It is not that complicated. Like, again, we call it an electro-mechanical device. It is, yeah, there's no electronics. It's just very basic, like current that will at some point manage to light like one lamp at a time, and a keyboard. That's it. It is really simple. And yet, with that simplicity, we can achieve an interesting amount of things. The thing that actually caught the interest of the German militaries in the 30s is that it's self-powered and it's portable, which means like it has its own AC battery included with it. You don't have to have like a power plug running with you, which means you can have it with you in the field. You can put it at the back of your command truck. You can put it in a submarine, and then suddenly we can discuss with HQ almost in real time. And nobody is the wiser about what's happening. They don't know if you're coming for them, if you're about to flank, or if you're in full retreat, and they don't even know how many you are. It is really powerful. And since the only thing it enciphers is text, like keys A to Z, it is perfect for most messages, which is the primary form of communication over radio at the time. They don't really talk to each other because, again, you can't really encipher talk in real time. That would require way more modern technology. But what you can do is send text messages and encipher them, which, I mean, to be fair, is not new. Like, we all know about, or most of us know about Caesar cryptographic cipher, right? Which is maybe the oldest cipher in the world. And that's the same idea. You send messages in text form, but you encipher them so that if it gets intercepted, nobody knows what's happening. Let's delve a bit into the details of the machine and how exactly it works. So as I mentioned before, this is rotors. This is what a rotor looks like. It's basically a wheel, a rotor that can turn. It has like a bunch of ratchets so that a mechanical arm can pull it. Every time you type a key, basically an arm will grab it and make it turn one. And what it does is that it has 26 electrical pins on each side. And each pin on one side is connected to one pin on the outside. And that's it. That's basically a substitution cipher in a small box. So yeah. By itself, not that complicated. It's not that hard to crack once you know the wiring, but it is the first piece of technology we use. The wirings are presets. You can't reconfigure them. They are numbered with Roman numerals, originally 1, 2, 3, and then 5, and then 8, and then 10 at the end of the war. And the wiring are preset, like factory made, and you can't change them because if you do, then your other party does not understand what you're trying to encipher or decipher. That's the basic thing. The interesting bit is that then you can start chaining them. So you have like some kind of an axle, and on that axle you put like 3 or 4 routers, And what happens is, since the pins are in contact between the various axles, between the various rotors, you go through the first, like let's say you get an input signal that matches like the here on the C. It will travel through the first rotor and exit at one of the 26 outputs, and then it will do the same with the second rotor, and then it will do the same thing with the third rotor, and then you'll get a signal out. And the thing is, like I mentioned this ratchet before, every time you press a key on the mechanical keyboard, it will just pull the rightmost ratchet one notch, which means the mapping will change because this one will turn 1, and so then whatever pathway was through for one letter becomes different. So, for example, if you keep spamming the same key, you will not get the same letter out of it. You will get a different letter just about every time. And that is one of the big difficulties, that every time you type one character, basically the configuration of the enciphering, internal configuration of the encipherment changes. So you can't make out patterns easily and other properties that really help breaking ciphers. And the idea is, after each rotor has completed the full evolution, it pulls the next one around, which also increases, like changes the pathway even more so. Originally, they turn every 26. The later wheels that have been made later in the walk turn every 13. So basically twice a rotation, the second one will turn. And then in turn, once it's at turn enough, it will make the leftmost one turn. That's the basic idea. But here's another problem that they encountered at first. Well, a problem. There is no printer, because if you had to have a printer, that would complexify a lot the machine. And you don't want something too complex. Again, it has to be portable. It has to be able to be on the field. It can be knocked down a bit and still work. That's hopefully what you want. You want something robust. And so instead of having a printer, the way it was solved is that there's a static reflector, a stator, if you will, at the end of the wheels, like the leftmost part of the machine is actually just 26 pins that are basically mapped one by pairs. So, for example, if it enters from the top here, it will go back between through one of the pins. And the idea is, since the signal comes from here, and then maybe let's say it comes back here, it will go back through the rotors again, this time from the right side. And since again they are still connected, one of the other 26 pins on the rightmost will get a signal out. Since you're guaranteed, sorry, I'm pushing the wrong direction. Since you're guaranteed by this reflector thing that the pin in cannot be the pin out, you're guaranteed that another path will be traveled through, and so you're guaranteed that the exit pin is different from the input pin, and that means that you can redirect that signal to one of 26 lamps, and then one of those 26 lamps will light up. And at the end, yeah. So what does the machine do is that I should have a picture. Yes, every time you click one of those keys, the electrical pathways will rearrange themselves because the rightmost wheel will turn. Then your signal will go through all of them, bounce back, come out again, and then light one of the other lamps. And that's basically your method of encipherment and your basically substitution cipher that changes every key. So, okay, you got that machine. How hard is it to figure out how many keys can you get? What's the complexity? So we have 3 rotors, and those rotors are not or you can put them out and put them back. It came with a really nice box on the original model. You had 3 rotors, and you could put them in any order. So that's 3 times 2 times 1. That's the many combination you can have, and that's 6. You have 6 combination out of it. Okay, that's not too bad. It's not great, but that's not too bad. Then you have how does the machine? What is the machine set up when you start typing the first key? Because remember, as long as you match the first key, since it turns every time, you are correct. If you do not match the first initial settings, then you'll just get garbage out. So that's 26 times 26 times 26, which is about 17,000 and a half. Cool. So if we multiply those 2 numbers, that's about 100,000 possible combination. For something that is built in the early 1920s and is really simple in its conception in terms of moving parts and tech, that's not too bad. It's unlikely that you'll be able to try out 105,000 combinations by hand if you manage to intercept a message and figure that out, right? You can, any normal substitution cipher, you can break it by you can break it by hand if you want to. You have to just try a bunch of combination. this thing is already out of the human possibility. You will have to use some other mechanics, or maybe find some kind of a failure in the cipher, or a special property of the cipher that allows you to reduce that problem space. Nowadays, it would be trivial to crack. But of course, we're not in the 20s. And when the war started, we were not in the 20s. And when the war ended, we were not in the 20s. So they've upgraded it a bit. So the first thing they did is that each of the 26 rotors has a ring setting. And what does the ring setting do is that it lies to you when you say that the rotor starts on the A configuration. As it turns out, it's not on the A internally, it's on any other of the 25 settings you put it in. And one of the main things it does is that it changes when the next rotor will be pulled out. Because remember, every 26 characters, every 26 turns, the next one turns. But you can't, by default, it's on the factory position. But if you turn it, then the first time the next wheel will start turning will be different, and that will break like cycles in the cipher. And yeah, that's one of the ways you can improve that. But of course, that wasn't enough. So what the military came up with in the 30s was to add a plugboard. And the plugboard is just a remapping. Basically, you have inputs and outputs, and you just short them with wires. And the idea is originally 6. You take 6 pairs of letters and you just scramble them together. So you apply an extra substitution cipher on the input and the output. So as every time you press the A key, for example, you can see on this one that the A has been connected to the J. Every time you press, is that the J? Yeah, that's the J. Every time you press an A, what Enigma thinks you get out of it is you pressed is a J and not an A, and then whatever letters comes out also gets scrambled this way, and then another lamp lights up. So that increases the cipher space of the whole operation. And of course, 6 pairs was not enough, so later in the war, we upgraded 2 pairs, which just makes the combination harder. And then another thing that is trivial to do is just create more rotors, right? So at first there was 3. That was not a lot of possible combination. They added 5 more over the course of the war, number 1 to 8. And then they were afraid that it was not good enough. So what they did is that they took the styler, or the reflector, the big bulk thing that is to the left of the machine you can see here. Well, you can't see it, but it's there. They said, what if we keep the same box, but we shrink the reflector, like we managed to maybe slim it down by half, and then we make a 4th rail that is also a bit slower, but still like technically compatible. It's kind of retro-engineered to work with the existing like box sizes and cases, because they didn't want to redo the whole production line. But that's just the cheap way they made to add like a 4th rotor that had 2 special wheels, I think were called beta and gamma. Who can be added. So that doubles your key space again. And also, since you added an extra key, then suddenly the key is 4 letters long instead of 3 letters long, which also multiplies by 26 the number of potential settings you have to guess. And that's the one that was used in submarines. It's called the Kriegsmarine M4. That's the Mark IV model of the Kriegsmarine. It's the one that the German subs used until the end of the war, and that was the hardest to crack. And since we're trying to say, okay, how much can we break of Enigma with a modern computer? I want to give it a chance. So we're going to use that one. So let's do some math again. We have 4 rotors out of 10, which is 2, because you only have 2 possibilities for the first one, times 8, you have 8, and then times 7 times 6. You end up with 672. That's a big upgrade from 6. Okay, now we have 26 times 4 instead of 26 times 3 potential like original possible key. So that's almost 500,000 possibilities. Then we have the rotor settings, because again you can actually internally offset each rotor, which also scrambles the output. There's no point in setting the ring on the leftmost one, because it makes nothing turn itself, right? One of the big thing about the rotor setting is that it changes when the next wheel will turn, which if you have nothing to your left, there's nothing to turn. So obviously there's only 26 times 3 and not 26 times 4. But that's still 17,000 extra combination that you're going to multiply. And the worst is this, because how many 10 pairs can you make out of 26? I'm not great at combinatory, but I trust Wikipedia, and that's 150 trillions. That's a lot of numbers. That's an insane amount. And if we multiply all that together, My Windows calculator says it's about 8 times 10 to the power of 26. So an 8 with like about 26 zeros behind it. That I can't even remember what kind of quantity that is in math. It's big. That's bad. But you have to remember it's big. And if we do a log 2 on it, we get about 62 bits. So you can roughly say it's a 62-bit key. Like you can express that in the way of a 62-bit encryption algorithm, which again, for a bunch of rotating wheel, few wires, a lamp, and a mechanical keyboard is kind of amazing. Like I have to admit, this is a lot that you can get from very, very simple like pre-computer era tech. So now the question is, okay, we have 62-bit encryption from the 40s. So how does that work? Before I explain how to crack it, let's see how that works. So to set it up, you install the routers. Initially, the router order was changed monthly. Later in the war, they improved it to weekly and daily because they were afraid that maybe the other side could potentially crack it one day. You set the ring settings. They are also usually not changed only once per day, sometime more often. And then you also set up the Plugboard. All those settings have been pre-agreed by both sides. So you both have a code book with the dates, and for every date, they tell you which are the codes that you're supposed to use. It's an equivalent of like, what is the input key, basically, to be able to talk to the other side. Once everything is set up, you set your routers up to the position of the key of the day. And then instead of immediately typing your message, you type another message. You just type 4 characters, which is an actual key. So for example, you'll pick like any combination of 4 letters and you will type it and you will write it down. And then you will reset your initial position to the key you've chosen. And then you will type the message and append it. The reason you do this is that if a lot of messages are sent the same day with the exact same settings, you might start finding similarities. Like for example, if some phrases or words happen to exist on several messages on the same offsets, which might happen every time you talk military jargon. And like, for example, if you have like an introduction or a salutation or whatever else, something very common that can come back and back, you start getting like, okay, those two things are probably the same. We can do something about that. So to avoid the problem, what you do is to give your enemy less space to play with. Instead, you only encrypt 4 characters with the daily key, and then every message has a different key, and so you can't get similarities that easily. That's pretty smart. So how did they crack it exactly? Because again, we're talking about 60 bits and some change that they cracked without a computer. How did they do that? So, okay, so this is the 1930s. And before we even go to Bletchley Park, even we start talking about Turing, we need to talk about Poland. So Poland in the 1930s knows that something is up. They've looked at how Germany has developed over the past couple of years, and they know it's not good. It's not looking good, and it's not looking good for anybody, but especially for them. But there is a lot of German rhetoric against Poland that they start coming up. So they set up a cryptographic unit in Warsaw, and try to say, can you read the German ciphers and figure out what he says? And they set up this man, which I'm curious, tell me at some point if you know about him or not. His name is Marian Rejewski. He's a Polish mathematician, which I was surprised at how little he's talked about he's talked about in literature, but in popular culture, it will always jump to a lantern immediately. And I think there is something wrong in this, because Marian Rejewski, in like between 1932 and 1939, he managed to reverse entirely like the Enigma machine used by the army, only using the German army and German codes in general, only using sales documentation. Like later in the war, they knew like the wiring of the routers. Maybe they had captured the machine or whatever. He did not know any of that. He didn't have access to spies that could steal a machine from like a sunken boat or just like a capture during a campaign. The only thing he had was some encrypts and decrypts from the sales documentation of the German corporate Enigma, the one that was sold for the public markets. And just based on that, like looking at how the sales speech was telling about how Enigma is good, he managed to reverse engineer all of the first 5 orders they made. And then he designed a thing called the Bomba. And if you think like, wait a minute, Bomba sounds a lot like bomb. It's because it is, and it is a machine that helped him crack it. And all his secrets he shared with the Allies in 1939. So here's a Bomba to the right. This is the schema he made at the time. It's called the Bomba cryptologist. My Polish is terrible, but yeah, it's a cryptologic bomb basically. And what it is it's a simple machine that is there to look at some specific properties of the Enigma machine. So German operators in the 30s had a weakness in the way they transmitted messages to each other. Every message that they sent, they repeated the key twice. It was done because they were afraid that maybe the radio operator on the other side would not be super used to it at first, and you might like get some of the first letters of the key wrong. And if you get that wrong, there's nothing you can do. Like if you get some keys wrong in the actual message, you can probably make out what it means anyway, because like you will have 1 or 2 letters that are garbled, but everything else will be proper German. But if you garble the key, then there's no way you're going to decrypt anything. So what they did was they repeated the key twice, but that gives you an interesting property that tells you that in your decrypt, the first and the fourth character, the second and the fifth character, the third and the sixth characters, or if you count from 0 to 3, 1 to 4, and to 5, all the same character. They should decrypt the same. So what did Rejewski and his team do? He built a simple machine that simulated what Enigma does, and he just plugged it in a way that if a key ends up with that property, he can stop, he's found the settings, that's done. And then since there is like 6 potential router configuration in terms of orders, because there was at the time only 3 orders, the solution was, okay, build 6 of those machines. Each one of them is like one of the 6 router orders. And then they're just going to try every combination like really quickly from a message until they manage to get this property. And if this property is valid, there is a very solid chance that you got the actual daily key. And then you can just try on an actual machine to see if you got it correct or if the output is gibberish. They had 6 of them, and until 1939 they used it, and they could read most of German traffic at the time. This was later refined because, as I said, it was shared with the Allied just before the war. And so basically Turing and his team, learning from Rejewski and his work, built the British bomb, which is basically the same thing, except it's more configurable. Because the main problem that they encountered is that in the 1940s, Germans started wondering if the repeating key was not a problem, and so they stopped. They stopped repeating the key twice, which meant the Bomba could not work anymore, and they had to look for other properties in the message to look at potential decrypts. And so what Turing did is that he refined the concept of the Bomba, and instead of like a hard-coded like those characters should be the same, he tried to decrypt those characters should probably be this at this position. And then they started relying on common formalities and expressions that were common in many messages a day. And as soon as one matched, then they could reverse engineer the daily key, and then they could decrypt everything else. For example, a very classic thing that German message did at the time was start by A and X, and for and to in German, and X for space. That was a very classic thing that we always look for. Another one they found is that one of the German general radio operator was a very formal old school Prussian, and he always started all his messages with very, very formal pompous salutations, and he always used the same one. And they knew that every time he sent a message, mostly all they had to do is try to decrypt this message, and if they got it, they had the key for the day. It's kind of amazing all they managed to do. And again, through that, the Allies were able to read the German cipher for most of the war. And according to the archives, most decrypts took about a day, 2, 3 at most. And the amazing thing is that after the war, agents of the Abwehr, the German secret police and secret services, were interrogated by the Allies and said, "Did you know we broke Enigma?" And what they found out is that they had the doubt at several points, both in their services and also in the army and in the navy. They wondered if maybe the enemy was getting a bit too lucky knowing where the submarines were. So they made a bunch of investigation, and they concluded that it's theoretically breakable, but it's way too expensive to brute force this. There's no way they can do that. And until the end of the war, they were convinced that the Allies were unable to read Enigma. So, okay, That's a lot of background. That's about 30 minutes of my talk, a lot of history. Okay, they managed to do that at the time because they were really smart. They had they relied on like the knowledge of the messages being sent, etc., etc. And they had also some time because the Poles had like a couple of years before the war to try to refine the techniques. I had none of that. I had like a couple months to just passingly on the weekend look at how Enigma works, but I have a very big machine right there with 16 cores. So let's get cracking. Okay, I lied. There's more history first. So I need a data set for this. What I decided to choose is one special telegram sent in May 1945. It's sent by this U-boat, which was sunk off the coast of Norway in the last days of World War II. It was discovered only in the 80s and it was raised in the 90s. And what they found inside it was a bunch of like messages that had been just received before on the couple of days before the sub was sunk. There was no keys because the German was smart, and the key books were actually written in an ink-soluble solution that basically immediately dissolves in water. So if they get sunk, you can't get the code book out. But the normal writing was still available, and you can see it on the right here. This is the plain text that this is the enciphered message that they got. So in 2012, a man named Mathieu Ropert set up a project to try to crack this message, and he used something that was really big at the time. You know all those projects you have at home, like a SETI at home and cancer, you know, like pre-Bitcoin era, let's burn energy to do something. So yeah, he used the same serial concept that had been set up by other people called Enigma at home, which is the same idea. You install it on your machine, you join a pool, and they basically keep sending you keys, and you tell them if you manage to crack something or not. And in 2012, he managed to crack most of the messages using like this distributed thing. But again, this was 10 years ago, and I don't have like a whole pool of machines. I have one machine. Can I do it? So we're going to focus on one message, technically called like P103681. It's about 372 characters long. So it's pretty good. It's not, I'm not setting myself with the hardest thing, like 10 characters long, 20 characters long, because those are really, really difficult to break. But it was initially cracked in 2012, and we're going to see, can we manage to decrypt it? So here's what it sounds like. This is Enigma. So this is literally gibberish. This is the output you get from an Enigma encipherment. You can't tell what that is, right? It's completely nonsense. And here's the decrypt. And at first you might be like, this is still gibberish. And I'm like, yes, but that's German gibberish, and it actually makes sense. And if you start looking closely, you might see words like Reichsmarschall, Göring, Führer, Admiral, Reich, and Bormann. And if you know anything about World War II, you're like, those people are Nazis, aren't there? And like, yeah, they are. And yeah, that's what they're talking about. So it is actually German. It is just that there's a lot of radio operator jargon in it, so it's a bit hard to read. But basically what it says is sent in early 1945. And it says the Grand Admiral Donitz, the Grand Admiral of the fleet, is now in overall command of Germany. And what it means is all the rest of the German leadership is gone. They're either dead or captured or running away. And the country's in its last leg, and they will literally surrender like 3 days later. And you can see Don is not looking too happy around the British a couple of days later. So, okay, this is an interesting telegram. It tells us about an interesting historical event, the end of World War II in the German High Command. Okay, now we're done with the history. Can we get cracking? So let's crunch some numbers. We would require to crunch about 10 to the power of 26 combination, 27 if you want to round up the 8. That sounds big. Okay, let's cheat. Let's start by ignoring the Plugboard. Maybe we can find a way to crack it without the Plugboard, and then we'll come back later to the Plugboard. We go down to 5 trillion. It's still a lot, but at least it's a number I can understand, right? 5 trillion, I even know the quantity word for that. I don't know the quantity word for like 10 to the power of 26. Okay, now we can try to cheat even a bit more. We have 4 wheels, and the third one will basically almost never make the 4th one turn, because for that to happen, you would have to have a lot of text being typed, and we know that those messages are like 300 characters long at most. So we can also ignore that and reduce the key space by 20, the setting space by 26. So we get 208 billion. That starts to be a number that I wonder, like, I can't remember off the top of my head how many cycles my computer can crack, but you know what, 208 billion, let's go. Let's see what happens. So we're gonna go for every possible Rotor permutation, right? It's a simple, like 4 for loops. Then for every ring settings, 26 by 26, we only try the two rightmost rings because we just assume that the other ones are pointless. Then we're going to try every key in the world, which is like, again, for four loops in each other. And then we say, okay, did we match the plain text? You might seem like, Matthew, that's cheating. You're not even trying to figure out if the text is legible. I'm like, I could, but I'm going to take a shortcut because we only have like an hour to talk about this. And also, that's a technique that was widely used in the war because it was common that announcements would be repeated over like less secure channels because they were big announcements, but when they were sent to like U-boats, they were sent in an enciphered way, and that was used during the war for if the length matched exactly and the times were about correct, they tried to see maybe that's the exact message we got. So that's what we're going to do. Okay, so how does we simulate an Enigma machine? So that's kind of easy. We have an array that just simulates like our Plugboard connection. So we take the input, we subtract A because the input is in actual ASCII characters and we just want to have an offset from 0 to 25. Then we go through the first, the rightmost rudder. I'll get down to the details. Don't bother too much about the code. Then we go to the second rudder, we go to the first rudder, we go to the leftmost rudder. And then we go through the reflector, because as you remember, you go through each rudder once and then you go back. And then we go back on the other side. And then we go through the reverse of the wiring. We have a lookup table that helps us making the path in reverse from the left to the right instead of the right to the left, which is basically the reverse of the table. We do that for the second, the third, blah, blah, blah. And then we have an entry stator that is just a technical detail. I'm not going to bother with it. And we go through the Plugboard again. That is basically the loop that we're going to run like 8 billion times or 200 billion times to try to see if we get something that we like at the end. Okay, so is there something interesting to do? You've noticed that there is a weird like offset math somewhere that looks a bit weird. So how do we implement the rotor, right? It's simple, right? The rotor is just 26 character string. And for basically, it tells you for each character, which one characters you get out. So the first thing we'll do is that we'll generate the forwards in the wiring array by repeating it 3 times. I'll explain to you why 3 times later. And since we are trying to use modern C++, we'll do that at compile time. And we want to avoid a modulo operation. Let me explain that to you. So here is your Enigma wheel, right? So you have your Enigma wheel, like this. So, you have A to Z characters, and this is what gets out. This is the first one of the set, the number 1. So, for A, you get an E, for a B, you get a K, etc. And every time I type a character, that wheel turns, right? So the mapping changes, the substitution alphabet changes. And I can continue like that, and, it will just do that until it cycles back to its original position. So how do we implement that? That sounds pretty trivial, right? You take the wiring. You just you take the offset of the input plus the offset of the ring, because the ring settings are scrambling the thing internally, and then you map it out. That sounds good in practice, but there's a bug. There's a bug in there. It's that between the offset and the input, you can end up reading just a bit past the end or after the beginning. So of course you don't want to do that. So you add a modulo, because again, this thing is it's a cycle. It turns. So obviously, you compute which offset you are, you modulo 26, and then you get the output. That sounds easy. But here's the problem. Here is modulo 26 on Godbolt on I think that's MSVC. That's MSVC 2022 with full optimization. I'm not an expert in assembly, but that's a lot of instruction to do modulo 26. There's 2 multiplication, a bunch of shift rights, a bunch of subtraction. That doesn't sound great. And luckily, I found a cheat by looking at how Enigma at home was implemented. And what they do is that they're smart about it. They duplicate every wheel wiring or rotor wiring 3 times. And what it means is that you take the input, you take the offset, and you add 26. So you aim to usually be here, that bit. But if you're not, if you're just a bit far off to the left or to the right, you'll still add up to basically the equivalent of if you had a modulo, except you don't have to pay for a modulo. And if you want to look at the decrypt, at the assembly generated, this is the difference. So to the left is doing a modulo, to the other, to the right is copying the same exact code, but and adding 26 with a duplicated wiring. And if you notice really if you look very scrutinized, you'll recognize that it's actually the same code, right? This is the lookup. The lookup is those two instructions. You're gonna have to do them anyway. The only difference is that you have a plus 26 that is added to the instruction. And to a modern CPU, that doesn't make any difference. Intel and modern CPUs can, like, adding a constant to two registers in a math operation is the same thing as, basically, that constant can be 0 to any constant you want. It's still a constant. It's the same CPU cost. But what you avoided is all the instruction on the left. And that makes a huge difference. I don't think I kept the numbers from my first iteration without the modulo, but I can tell you it was way slower. So here is our first attempt, right? We tried to crack that amount of permutation, 2 by 8 by 7 by blah, 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 blah. Okay, like, let's see we're really unlucky. And basically, like, the match is like the last setting we'll try. Okay, 208 billion. So let's run it in my first implementation. You can see it tells you just about how many combinations it can try per second. I mean, those modern CPUs aren't bad. They can try 1 million combinations per second. That's not bad at all. But my ETA is 3,000 minutes, which it's about 52 hours to exhaust all the combinations. That's technically within what the Allies did during the war. But can we do better? Because come on, like 3 days. I don't have 3 days. Like we have an hour together, and we're already 40 minutes in. So what if we use multi-threading? And I remember I said I had 16 cores. So mathematically, if we divide it by 16, it should be 3 and something hours instead of 15. That sounds better. And since we're using modern C++, we don't even have to like add a third party or anything. What we do is that we just generate an array of 26 characters that are basically 0 to 26. And instead of doing like my normal for loop 0 to 26, we do this for each instead, which is basically the exact same thing. Except we add the std execution parameter to see it's parallelized and then sequenced. And that's it. And I tried on my machine and I could see my quantization. I had my 16 cores like cranked to the max. And I got about 2-3 hours. Really simplify. And I enjoyed the fact that I could just get that by adding like a couple lines to my code and a minimum refactoring. But still not good enough. 3 hours and a half. Come on, like this has to fit in the talk. So let's try to be a bit smarter. Let's start to maybe take some hints from what those people who were cracking Enigma all day for years have tried to do. So if you look at Enigma, the first order, the rightmost order turns all the time, right? Because every time you press a key, it turns 1. But the second one, it's gonna turn a bit. But it only turns every 26 characters or every 13 characters. And the third one, well, the second one, if you count from the left, sorry, the second one, is going to turn even less because it has to have like both cycle through the third and the fourth before it turns even 1. And so basically it's in the same position for in between 169 keystrokes at best and 676 at worst. Which means for most messages, it's not going to turn. And if it turns, it's going to turn maybe 4 times. And even less than that, because our message is like 300 and something characters. Like it's going to turn twice at best. So you know what? Let's do something simple. What if we just assume that the ring setting on that is 0? And then we'll just say, you know what? If we got a quarter of the characters right, then we're probably there. And the only thing we have to do is fine tune the ring setting to actually turn at the right pace. And then we're good. And fine tuning is easy because it's not part of the main like 10 imbricated for loops. You can do that once you're done with that. So we divide the search space by 26. And then after that, we have a second pass that is just gonna fiddle with the settings, maybe like 26 by 26 time, which is nothing on a modern computer. So here is it. Once we have found a partial match, we just try like the 26 by 26 resetting combination. And then we only have to search 8 billion in the first pass. And hey, look at this. It's about 6 minutes to find it. Because now we can try about a bit more combination. You will recognize that some of this math is probably incorrect. I based all my estimates on the Windows copy function. So it's probably wrong most of the time. And you're like somewhere between 1 and 3 times the actual value. But, you know, even if it's 10 minutes, I can live with that. But then someone is going to come back in the audience and say, but what about the Plugboard, Matthew? You kind of cheated. You just say, okay, what if we don't consider this a million trillion extra complexity and then we crack it? Like, that's cheating, right? So we can't brute force 150 trillion. We barely could brute force billions. So how do we fix it? And here's an interesting property that was also found by research at the time. You know that you scramble 10 pairs together, but you can look at it the other way. There's 20 characters that are scrambled, but there are 6 that are correct. So in your decrypt at the end, even if your Plugboard is wrong, because you basically have not plugged the right characters, 6 of them would be in the right place. And then what we can do is say, hey, let's look at the matches letter by letter and say, hey, how many letters of the same kind have we matched? If the top 6 matching letters or like the highest we got as some kind of index, then maybe we're onto something. So, for example, here's the message we're trying to crack. At the bottom, you can see the pairs that were plugged for that day. So A was E, B was F, C was N, blah blah blah. And at the top is the amount for each letter of how many times it ends up being correct in the decryption without the setting. So if I have all these Plugboard setting wrong, which is like I did not set it up, I still get a bunch of them that have a high score. And the green ones are the correct one, like G, I, K, M, O, and T, and Y, or not a stacker, as we call them, because that's the Plugboard is called stacker in German. They're not plugged together, so they're correct. If I get a G on the output, it is actually what I'm supposed to be reading. And if you look at the number, there's like 6 correct here, 5 correct here, 4 correct here, and most of the other ones are just garbage. Like they're 0, they don't count. I have a bunch of false positive on A, E, and S, but that's not completely surprising because A and E are stick together. So that's probably why, and also they are very common letters. And so as it turns out, that's good enough. I tried a bit and I said, you know what, if I tweak the heuristic and say that score ends up to be about bigger than 1/10 of the length, which is, 6 to 26 letters correct, we don't really need to do the Plugboard. We can just cheat and say, hey, if I get 1/10 correct, assume we have found the right setting, and then you just have to tweak the Plugboard in a separate pass to figure out the rest. And so, can we do better? And I'm like, wait a minute. We know how we cheated and said we can ignore like the second modern term. What if we also do that for the third one? That's like, it will be wrong, right? Like it will not turn at the right time. And so I will be out of phase in the wiring. And so every amount of characters, the decrypt will be wrong until it turns, and then it will be correct again for like about up to 20, maybe 20 or 10 characters. And then it will turn at the wrong moment, be wrong again until I catch up and turn too. And again, that means that you're not entirely wrong. And if you start getting a pattern here, it's because Enigma kind of work like Wordle or Mastermind if you're an older person. If you get the setting mostly correct, it tells you, hey, you're not too far away, keep digging. And that is maybe the main weakness of this system, is that it's not a clean 62-bit key. Because modern ciphers, if you get 1 bit of the key wrong, you get absolute garbage. And there is no way it is, you can't tell that from noise. While with Enigma, due to the way the machine works, a lot of the time, you can actually find a heuristic that tells you, this is a noise, this is just partially correct. Keep tweaking. And so we keep tweaking. And then we add an extra fine-tuning pass. And let's see, that sounds pretty fast. I log every 5 seconds, by the way. And hey, I got it. The rotors were 5, 9, 9, 5, 6, 8. The ring setting was 0, 0, 17, and 1. And the key of the day was YOFZ. And there we go. We got it. So I didn't do the math. So my heuristic works with this message. I didn't try it with a billion messages. If you know anything about cryptography, feel free to take a look and tell me if I'm wrong, because maybe I am, but I think I'm on something. I'm onto something. Although I have thought about testing something else, which is called the index of coincidence, which is a thing that is used to crack ciphers, especially older ciphers, which basically looks at the text that is potentially partially enciphered and says, can you tell if the frequency of the letters is different from the normal distribution of like pure random? And as it turns out, it might be working because I know it worked for other ciphers. And also, if you're a purist into Enigma cracking, you'll say, oh, but this is not a ciphertext only attack. You already knew the answer and you just had to match the key. And I'm like, that is true, but I also spent like 40 minutes explaining how Enigma works and how this basic thing could crack it. I don't think it would have fit an entire talk unless I was talking to a crowd that was already like fan of Enigma Decrypt and could tell me how they would have advanced it. Some people have done that. I encourage you to look it up if you want to. And again, this is not an end command attack. A lot of the cracking in World War II was about, hey, we probably guessed that some of those letters are there. Can we just find a match and then see if it works? So we used some C++, right? One of my goals in this project was to figure out, hey, if I try to do like a small project on the side and I plug in like C++ latest in MSVC and I get like C++ 20 out of it, like how many modern features will I get up using in this small pet peeve project that is about like, I don't know, it's a couple hundred lines left and right. So we use C++ constexpr and C++ 20 constexpr algorithm a bunch. As I mentioned before, the rotors in the core of the code are just like, it's a string of 26 characters. And then using constexpr, we create the repeating mapping table and the reverse repeated mapping table. And all of that is done at compile time. I looked at how they did it in the old C project, and they just copy pasted the same string 3 times, and then they copy pasted the decrypt 3 times. And that's way more error prone than this thing that can just at compile time take 26 characters, say, okay, is there any repeating character? There shouldn't be because it's supposed to be a one-to-one mapping, and then build everything for me. And that's way less error prone. I use string view and span a bunch, especially string view because all the messages are string and the decrypts are strings, and you don't want to allocate every time. So using string view was pretty useful. And finally, span was also used a bunch because I kept passing like arrays of like settings and stuff. And this is every time you're like, do I need a copy? Do I need to pass a vector by reference? I just use a span. And again, parallel algorithms helped me like make this thing from single threaded to multi-thread by changing like 10 lines, and I was done. And no third party. I have considered using other things. I've been wondering if maybe like iterating through the rotor combination at the top, you know, like the 2 times 8 times 7 taxes. Maybe I could write a generator using ranges, but I was not super comfortable about it, and I'm not writing a talk about ranges, so I kind of skipped it. For the same reason, but even worse, I did not even try coroutines. I watched a talk on coroutines 2 days ago, and I think I gave up after 30 slides of glue code. Like it would have been a talk about coroutine if I just implemented a rotor of coroutine. So maybe in the future, but no. And the big one I miss, and I hope Hodin is not in the audience. Sorry, Victor is not in the audience watching this. I had entirely forgotten that C++ 20 format was actually format was in C++ 20. I thought it was in 23. So my code is full of couts, and I really apologize for that. I will rewrite it at some point using stud format because there's no excuse. It's there now. We should use it. Cool. So what did we do? My first takeaway is that Enigma is not a recommended cipher in 2022. If you were considering using it to encrypt all your personal data so the government can't track you or your ex or whatever else, do not do it. Not good. You should stick with RSA and AES and everything. They're way better. A true 60-bit cipher though, like a true 60-bit cipher will not be broken by my machine. I mean, I'm pretty sure the NSA and people with a lot of means or like a bunch of machines on the cloud can brute force a 60-bit cipher with enough will to do it. But a proper 60-bit cipher on just one machine, I don't think there is like the CPU will not be able to crack it fast enough before we all die of old age or something. And finally, I think you can see that some C++ 17 and 20 features will find their way in even the smallest hobby project. Because again, like that thing is not that long. There's a link to my GitHub at the end, and you can find in my different like pet peeve project, one of them called Enigma. That's the source, and you'll see that just fiddling around this talk, I ended up using like C++ 17 and 20 features that are really easy, like span and string to go everywhere. I could use some of them. That was pretty good. Do you have any question? But actually, I know questions are going to take a while to appear, and I already know that there's one question that we should already have and that you have that should be answered. So I'll go ahead and do it immediately because we only have 5 minutes. So, because there's one big question in this talk. There's one big question that has not been answered, and I think you want it. And the real question is, what happened to Wojewski and the Polish Cipher Bureau? Because if you're anything like me, you started this project thinking, yeah, Alan Turing, the guy who invented the computer and broke Enigma all by himself at Bletchley Park. Who is this guy, Wojewski? I've never heard about him before. So what happened? Why have we not heard about him? Because if you look at the slides I had earlier, he died in 1980. So it's not like he died during the invasion of Poland or anything else. So what happened? Let's find out. Because the story is not over. If you remember, July 1939, the Poles know that the writing is on the wall, Germany is about to attack. So they go to the Allies and say, here, we cracked Enigma. There you go. It is interesting to read the reports from the British at the time. Like they fell out of their chair. Like a guy comes up and say, hey, by the way, this is the German cipher. We cracked them. Have fun. They say, I think Dilly Knox, the guy who was in charge of Bletchley Park, said that it set them up at least an advance of 2 years. It saved them 2 years because they just had everything. And again, the Allies spent a lot of effort breaking Enigma. And so why are we never talking about Wojewski? What happened to him? We have 4 minutes to answer that question, and I have a bunch of screenshots from my game. So this is Poland in about September 1939. Things are about to get really spicy for them. Germany will sadly attack them in a couple weeks with like an insane amount of division. And sadly, they will reach Warsaw in about a week. And this is the start of World War II, sorry. So Wojewski is there. He's in Warsaw, and the Germans are about to attack. He just shared his secrets with France and Germany, France and England. What does he do? Well, the Poles are not stupid, right? They have been reading Enigma for almost a decade at this point. They know that they are coming. So as soon as the Germans start looking like they're going to advance to Warsaw really quickly, they burn down everything they got, they dismantle everything that they can't move, and then they put all the cryptographers in a train and they send them to the Romanian border because Romania is still neutral at the time. They are leaning toward the Axis, but in 1939, they are still neutral. And they managed to cross with a bunch of Polish refugees. Sadly, seeing that amount of refugee coming up starts startling up the Romanian police, who start considering arresting everybody until they can figure out exactly who's there. And the problem is, the Poles know that Romania is leaning toward the Axis. They probably have spies or informants for the Germans in their rank, especially in the police. And so if the German learns that 3 Polish cryptographers have been caught at the border, they're probably going to take an interest in them. Luckily, there is a lot of people at the border. There is some confusion in the evening, and our 3 Polish friends managed to slip away into the night, buy a bunch of tickets, take a train, and go to Bucharest. They show up in Bucharest about 20 hours later, and they run to the British embassy as fast as they can, and they knock, hey, we broke Enigma, can we get in? And the English are like, sorry, old chap, never heard about a Polish guy who broke Enigma, we can't enter. And they just send them home. They get a bit panicky after that, but they don't lose hope. They go to the French embassy and say, hey, for the Polish, we broke Enigma, can we get in? The French are like, I haven't heard about you, but I'm going to call Paris just in case. You know, we're French, we like to cover our backs. And he does, and they immediately say, yes, let them in. And so using some diplomatic passports, they managed to make them move to Paris. And they immediately put them on PC Bruno, which is the French cryptographic team. And they start cracking more things. And over the course of the coming year, they would crack basically advance notice of the attack on Denmark, Norway, the Netherlands, France, and Belgium. The Allies will never make use of it, sadly, but they managed to do a lot of that. And also review some cryptographic ciphers that the French are working on that turned out to be really bad. And finally, they will receive a visit from Turing himself and basically explain all they did, everything so far. But the story is still not over because sadly, Wojewski's luck is really bad. And as it turns out, he just left a country about to be attacked by Germany for another country that is about to be attacked by Germany. And as we all know in school, France doesn't fare that well in 1940 when the Germans attack in May. And in about 2 weeks, they get defeated. But again, the French cipher decide that it's too dangerous to just let them around and do nothing. So again, they dismantle everything and send him to North Africa. A bunch of people will be captured, more like minor clerks and things like that. But some of them will be tortured, and none of them will ever betray that there were a bunch of Poles there and that they had the secret to Enigma. Amazingly. After the fall of France and the puppet regime of Vichy is set up, the French resistance will help him move to Free France, in which he will continue working on some cipher for about a year or two. Sadly, at some point, Germany starts thinking that Vichy France should basically be Germany, and they invade France again in 1943. But this time again, Brzezinski still has France. And so he goes to the Spanish border, and they give him a guide that will allow him to cross the Pyrenees, the big mountains that are in southern France, and get to neutral Spain. Sadly, the guide turned on them. He robs them of all their money, and he lets them crossing the Pyrenees at night on their own, which they still manage to do, but are arrested by the Spanish police, who send them in jail in Madrid. He spends about a couple of months in Madrid, until the Polish Red Cross helps him get out of jail, saying like, well, you're holding mathematicians for Franco, that's not okay. And he managed to negotiate their release. They go to Portugal, and finally, in late 1943, they arrive in England. And you're like, finally, right? It's gonna work at Bletchley with Turing. They cooperated before. Sadly, the Brits again are like, sorry, old chap, but Ultra is a national secret. Only Brits allowed. We cannot afford to have a man who lived like 3 years in the Maquis in Vichy France to work on Enigma. And basically, they put him on a small desk job, and they ask him to crack minor ciphers, which must have sounded like Sudoku to him. And it is really sad. And this is probably why you never heard a biopic of Rojewski's, is because the story does not have a good ending. Because he's not allowed to work with Turing for the rest of the war. And after the war, he goes back to Poland, which is occupied by the Soviets. And since he suspects that if he tells anybody that he cracked Enigma in 1940, the Soviets in turn will take an interest in him. He just shuts up about the whole thing. Nobody talks about the Cipher Bureau for 20 years until he publishes his memoirs in the 60s. And of course, the English also keep everything about Bletchley's secret for about 20 years or something. So nobody knows anything. And this is why we never heard about this man. But what if? I keep wondering, what if? What if the Brits recognize the genius of Rojewski and allow him to work with Turing? What if Turing is what it's not just Turing who makes the bomb, but also ENIAC? What if they work together and create the first computer? Imagine what we could have today. We could have like cons by default nowadays because two great people worked on that. We could have no such thing as ill-formed, no diagnostic required, or whatever the hell that means. We could have had coroutines in the 90s, and maybe there would even be library support. Like, who knows we would have gotten. This is my, when we talk about high history, this is my kind of kink. Like, alternative Orban, boring. Rojewski worked with Turing at Bletchley, now we're there. And I'm just a guy who likes alternative history, but if you happen to like alternative history and also code, we can pay you to do that. So you should consider joining us. And with that, furthermore, I think your build should be destroyed. Thank you.